of the University of Michigan about online markets and social.
So thank you, Stephen, and thank you for the very kind invitation. So I'm going to talk about online market with social signals, and this is joint work with a number of my long-term collaborators, Manuel and Gerardo, and some of my students or former students. All of the people on this list are actually Spanish-speaking, so every time I have a meeting, I feel really bad. So the story behind this work started with a conversation that I had with Manuel, who is at the MIT Media Lab a couple of years ago. And I asked Manuel, what is, if there is one paper in computational social science that I needed to read, which one would it be? And Manuel told me to read this paper. And this is a beautiful paper by Matthew Seigelnick, Peter Dodds, and Duncan Watts, looking at social market with social influence. And it's very nice for multiple reasons, and I'll tell you only one of them. And so that's the next thing that I'm going to do. And so we started working on this for about 3 or 4 years after that. So let me tell you why this paper is interesting. And so the World Wide Web obviously has changed the way we are doing shopping. This is what I got from iTunes a couple of years ago when I logged in onto it. And so obviously iTunes is trying to make you buy some of these albums. And this is what they recommended to me. No, I'm not listening to any of this stuff. You can see the song that I was listening on, to at the top. But essentially one of the things that iTunes is doing is choosing a couple of things that they believe you are very likely to buy. If you book a room in Ann Arbor in Michigan and you use Orbitz, for instance, you would get a list of potential places. And one of the things that I want to mention here is that this list is typically ordered. And the positions obviously are very important because humans are typically looking top down and right to left, at least in the western part of the world. So the way you display this product is very important. Obviously, you have recommendations for all these products. You are very well aware of that. And if I go back to iTunes again, one of the things that you see on this particular site is you see the popularity of the various songs in this particular case. And this popularity is actually a normalized market share. And one of the things which is interesting here is that you see the first song. This is a U2 album a few years back. And this is the first single of the album. And what you can see is that it has a very large popularity signal, although the song is not very good. It's actually too complex. And it's not as good as some of the top songs that you see at the top of the list here. So you have all these social signals. You have all these things that you can play with. And so what Seigelnick, Dobbs, and Duncan Watts did was actually trying to explain why these social signals are actually doing certain things to the market. And their starting point was the fact that it's very difficult to predict this cultural market when you buy books, when you buy movies, and things like this. And there are plenty of examples that you can have of people rejecting things that became very, very popular later on. And so what they did was doing this virtual laboratory where they were trying to understand the unpredictability and the efficiency and the inequalities of these markets. And to do that, they create a massive computational social science experiment using the web to study social influence. And I'm giving you the end of the story, but you'll see many aspects of it. But what they saw is that they could replicate all these inefficiencies, these inequalities, and this unpredictability of this market in this virtual setting. And so let me show you what they did. So what they did is a market for songs, and not for famous groups. So they were unknown groups, but essentially what they were listing is an order list or a grade of songs. And every one of these songs had the group name and then the name of the song. And they did something else that I will mention in a moment. They had the social signal as well. And then you could actually listen to these songs, and then afterwards you could decide if you actually would download the song, which means that you could keep it forever for free. And so some people did that, some other people didn't do that. And so to actually understand these markets, they took all the participants and split them in various worlds. And in every one of these worlds, people would have different social signals. And they also had a world which I did know by the moon, where you had absolutely no social signals. It's like you were alone in that particular place. And obviously, by looking at how these worlds were evolving, they could deduce what the market was doing. And so they basically So they basically looked at these two things, so the social influence condition and the independent condition. And one of the things that they show is these social signals, which was essentially the number of downloads. It's like the market share. I'll tell you later on that these two things are equivalent. But essentially, this was the number of downloads of every one of these particular songs. And they were ranking all these particular songs by these popularity signals, the number of times every one of these songs had been downloaded before. And they actually made a very good decision there because popularity is probably the best social signals. There were a lot of studies afterward trying to find out if recommendations were better or not. But most of the time, this is seen as the better social signals that you can send in these social markets. So these are some of the results that Duncan summarized about 10 years after they did this. And one of the things that he said is that the best songs actually never do very badly. They may do very well, but any result is possible. And the other things that that Duncan summarized is that the dynamics can be manipulated, but not easily. So these markets are very unpredictable, essentially. And so when Manuel showed that to me, my first reaction was that, what if we optimized? Because, I'm an optimizer by training, so I said, what if we optimize this market all the time? What would be the result? And would that change the predictability, the efficiency, and so on? Because you have a lot of things that you can optimize. Obviously, you can decide what you show, how you show it, what is the order in which you show these things. You can choose the social signals if you use it or if you don't use it. And obviously, you have to model the utilities. And so what we try to do is to try to see if we can optimize this market holistically using all these things and see what would be the result. And that's what we started to do. So let me formalize a little bit the problem. So what we have is this online market. Participants are coming, and they have the ability to sample a product. So they can listen to the song, or they can read some part of a book. And then once they have done that, they can decide if they buy the product or not. And so the popularity signals will influence only the sampling step. They will decide what they are actually listening to. It doesn't impact the quality of the product, obviously. And then the next participant comes, and you have to decide which products you show and in which order and which social signals you show. And you repeat that for a long time. And so Manuel, who I mentioned at the beginning, had actually worked with some other people in the Media Lab to try to formalize this. So they reverse engineer all the experiment that Watts and his colleagues did. And so they could find out what the visibility parameters were, the quality of the products, and the appeal of the products. And they formalized that as a generalized multinomial logit. And so what you see on the screen there is the probability for trying sampling product I at step K. And it depends on the visibility of the product, where the product is positioned. It also depends on the appeal of the product. Is this a product that appeals to you or not? And then the social signal here, which is the number of purchases that have happened in the past. And then you normalize this for having a probability distribution. And so this is what they did. And obviously, what we are interested in is maximizing the expected number of products that you're going to download. And this is essentially multiplying the probability of sampling a product by the quality of the product. And so we want to do that over over time, essentially. And mostly the degree of freedom that we have here is what social signal we choose, and also in which order you display this product. That's where the visibility comes in. Now, yes, sir.
Signals?
The visibility signal is this part there, this guy here. And this is where you position the product in the list. If you put something on top, it's much higher. The visibility is higher, so the probability of actually sampling it is actually higher. I thought you would ask another question, which is, what is the quality? Because that seems to be very subjective. But the quality here, we are using an insight from that paper as well, which is the fact that the only thing that we are really interested here is the probability of actually downloading a product or purchasing a product once you have sampled it. So that's what we mean by quality here. It's a quality at a particular point in time. That's the intrinsic probability of downloading the product or buying the product if you are actually sampling it. And you can estimate this very nicely using a Bernoulli sampling. And this is actually very nice because you learn the best, the best product, the product with the higher quality or the lower quality are learned very fast because the variance depends on the quality, essentially. So then we started optimizing. And the first thing which is very nice is that if you try to find the best permutation for all these products, you can do that in strongly polynomial time using a reduction to linear fractional assignment problems, and we can actually do better in practice experimentally. So you can solve these things for very large number of products very, very efficiently. You can do that in real time, which is nice. But this is just optimizing at every one of the steps. At every one of the steps, you decide which is the best ranking of the product, presentation of the product that you can have. And so that's a good news. And when you look at what does this happen in practice, this is based on the data from the music lab, you see two things. First, optimizing. Just optimizing with no social signals give you significant benefits. So that's just optimizing the visibility. So what you see here is the optimization approach. This is the popularity signal. This is not using anything like a random ordering. And then the second thing that you see, and this is on the right of the picture, is the influence of social, is the benefits of social influence. And these two things are cumulative. So if you use both optimization and the social signal, you get a much better market efficiency than if you don't. And so the other things that you can see is the predictability of the market. So this is essentially what Duncan Watts and his colleagues have said. So this is essentially what you see here is the quality of the products on the x-axis. Every one of these bars is a product. This is the number of purchases or downloads. And this is repeated over a large number of experiments. So you can see here that this best product can do very well or can do so-so, or everything in between is possible. That's what they said. So it's a very unpredictable market if you use the popularity ranking. If you use the optimization approach, what is very nice is that this market becomes highly predictable. So the best product here has a very large share of the market at that particular point. I'll come to you. The other products have less. And you can see that the social signals is giving the best product a very big boost. Yes?
I'm a bit confused by the quality which you're plotting on the top left.
Yeah.
But the quality is estimated from the data, or not?
Yeah. So you can just let people play. You can let the market go, and every time somebody samples that particular product, you can estimate the probability that this person will download the product, and so you get an estimation of the probability of downloading.
But then why isn't the plot strictly ordered by quality?
So this is so every one of the bar here is a product. And this is the number of times that the product is actually downloaded or purchased over a large number of experiments, let's say 200 experiments. So you see that this product once has been downloaded like 300 times and once like 250 times in another experiment. Okay? And this product was downloaded about 6,000 times in one experiment. In another one, it was like 200 times.
So you have those two bars and next to it this one dot. And those confuse me. No, to the left, further.
This?
A bit further. Further. Once more further.
This?
Yeah. So this one dot. Why?
This one? Oh, because this product was downloaded about 1,000 times in one of the experiment, and the next thing was like one left.
Yes.
Two dots.
This one seems to have not ever been downloaded very often, and
No.
the ones to the left have been downloaded.
Yeah. So I mean, I don't know. So there is some unpredictability here, right? So this is what they say. It's very unlikely to be predictable, right? And it's unpredictable. You don't see that when you are actually optimizing. Okay, you don't see that. This is nice. Okay, so optimization is nice, right? Okay. The other one is popularity ranking. It really depends on the initial condition, right? So this product somehow, for some reason in this experiment, that's what happened. Okay. So obviously we were like, Florian yesterday said, okay, so we have all these things behaving nicely. Can we prove something about it? Except that this is much simpler than what Florian is doing. But we knew nothing about this, so we started simplifying things such that we can prove things. And so the first thing that we did was using this quality ranking. You take all the products and you rank them by quality, and you present them that way. So the best product have the best visibility and so on. And so this is not dynamic at all. You just have a static ranking. And very interestingly, this static ranking, ordered by quality, behaved almost as well and sometimes better than the optimization approach. And it's dominated sometimes at the beginning, but then they tend to converge to the same thing. And so that was very interesting for us. And when you look at the predictability, this is what you see again. So you can see that the quality ranking, once again, is even more predictable than the optimization approach. So we were like, wow, this is interesting. So then we started proving things, and the first thing that you can do is to show that if you use this quality ranking, you can actually prove that the number of downloads is going to be increasing monotonically over time. And so in expectation, every time you maximize the number of expected products that you can download at every step. I mean, it's a fraction of a product, but you are doing better. And so this was interesting, and most of these proofs rely on the expected number of downloads and the relationship between the quality of the product and this. This is very traditional in these assortment problems. And the next thing that you can prove is that the market is actually going to a monopoly for the best product asymptotically. And I'll tell you a little bit how we prove this, but the intuition here is that you can model, you can model that like generalized Polya urn with reinforcement. So you extract a product, and then you put this product in a number of times this product inside the bins as well. And I'll show you a little bit more detail later on. So in a sense, when you use the quality ranking, we converge to a monopoly at the limit for the best product. So it's entirely predictable. And social influence is always good in expectation, and it is optimal asymptotically. And what I like is that it's not only good for the market, this is optimal for the market, but it's also very good for the customers because they are driven to the best product in a sense, the product that has the best quality. And so you can prove the same thing for the optimization approach. It also goes to a monopoly at the limit on the best product, and you can generalize that to assortment problem using some of the algorithm that David and Pat have used in the past. So as the basic optimization approach. So essentially all these things are nice. Okay. So let me tell you a little bit, let's try to make this a little bit more realistic now. And one of the things that people always complain is that, yeah, but you assume that all the customers are kind of homogeneous. What happens if there are different class of users and they have different kinds of appeal and different kind of utilities for every one of the product? And so this is, you can generalize this and know essentially what is happening is that the appeal of the product and the quality of the product is going to depend on the classes of users. And so you can ask exactly the same question, what do you present to the customers and are the popularity signal beneficial? And there you have bad news. If you try to optimize, this is NP hard under Turing reduction, so it's very difficult to do. And it's actually very difficult in practice, at least on the instances that we looked at. So we can't really optimize this globally. So what we can do is we can say, hey, let's average the quality of the product and let's reason about this. And the proof are nasty, but essentially what you can do is that you will always converge to the product which has this average quality. But unfortunately, showing a social signal for this particular product can actually deteriorate the quality by a factor of k, where k is the number of classes of customers. So it's actually pretty bad. It can be pretty bad. But there are good news. So what you can do is you can say, hey, if I segment the market, then things are very different. And many of the websites that you find there typically allow you to actually view the reviews by different categories. If you are single, or if you are a couple, or if you have children, and so on. And so either they learn these things or you can tell them the information. But if you know the type of a participant, what you can do is exactly do what we did for the homogeneous case and orient the people to the world they belong to, the category they belong to, and then you can use the quality ranking or the optimization approach to do that. And when you do that, you can show that you can improve the performance by a factor of k. That's in theory, and this bound is tight, and we can reproduce it on experiment. This is one of the experiments. And what you can see there is that social influence on the average quality can be really bad. And we can show also that social influence can bring very significant benefits when you do this. This is more than 100% benefits in a sense. So in a sense, even if you do market segmentation, the market is predictable, is optimal asymptotically, and you benefit from the social signals. Now, I presented this to a conference in social science, computational social science, and people were extremely uncomfortable with these results because you say, yes, you address predictability, you address the efficiency of the market, but you increase inequality substantially. And they asked us if we could actually mitigate that, the fact that you introduce substantial inequalities between the products. And so what we started looking at is, can you change the social signals to have a notion of fairness inside the market? And so what I'm going to show you, I'm going to show you the results here, but the result in terms of market share, which is really equivalent to the number of downloads. And so what I'm going to do is exactly the same thing. The visibility is there, but then you have a function now which depends on the market share, like in iTunes. And the kind of social signals that I'm going to look at is a polynomial of the market share. And so what we did so far is using r equal 1, but I want to look at r equal, smaller or equal to 1, obviously greater than 0. And so this is how the market share evolves, and this is going to give you an idea of how we prove some of these things. So this is the market share at step k plus 1 in terms of the market share at times k. One of the things that you see there is this random vector, which denotes the product which is downloaded in this discrete the product which is downloaded at a particular point in time. And then if you start playing with this, you can introduce the expectation of downloading a particular product given the current market share. And once you do this, you get this beautiful algorithm, you get this beautiful formulation here, which probably every one of you knows, which are this beautiful Robbins-Monroe algorithm. I knew nothing about this. But essentially what you have is that f is continuously differentiable here. The gamma k plus 1 there is essentially converging to 0, and if you sum all these things, they sum to infinity. And then the uk plus 1 is kind of the noise, and that noise converges to 0. And once you have this thing, you can prove, you can use this beautiful book by Kirshner and Ying, if I remember correctly, Yi. And the interesting story about this is that this person was actually sitting next to me for 22 years, and I never talked to him. I mean, kind of a quarter of a mile. And then I discovered this fantastic book afterwards. But essentially, if you want to know about this Robbins-Monroe algorithm, you read this book and you know everything. And so one of the things that you can do is use this, approximate this particular discrete process, stochastic process, with an ordinary differential equations. And you can study the properties of this continuous ODE. And so essentially what you do is you have so what you see here is the solution of the ODE and how it approximates essentially the market, the discrete process here. And so the only thing that you need to do is study this equilibria and then prove some convergence result. And one of the things that you can show is that if the social signal now is smaller than R, is smaller than 1, then all the equilibria are going to be these monopolies plus an internal equilibria inside a simplex, which really depends on the quality of the product. And what you do there is you assign a share. The market share is becoming proportional to the quality of the product. But there is no monopoly. So this is what it looks like. And this is kind of nice because this converges very quickly in the market. So the market converges very quickly to this equilibrium. And the best product is always at the top, and then all the other products depends on the quality. And so whatever the appeal of the product at the beginning, they converge to this nice market share. So you can prove this, that actually if you start with non-zero market share for every one of the products, you're going to converge to this inner equilibrium. And the way you do that is basically by induction. Because if you remove one product and you put it aside, the rest is still a Robbins-Monroe algorithm. So you can prove that by induction. And the other things that you need is essentially the key property of the continuous dynamics. So this R is smaller than 1. So this is actually converging to 0. And therefore, these two things are actually showing you that this is the market share equilibrium that I've shown you before. And so this is nice as well. So the market is predictable in this particular case. It has no monopoly, so the computational social scientists are much, much happier. And then it has some notion of fairness because the product of higher quality will have a larger market share, which is something which is desirable. And then the market converges to this nice equilibrium if the appeals and the quality are strictly positive when you start. And so the conversion doesn't depend on the appeal. It doesn't depend on the initial condition. You will always converge to this nice equilibrium. And the conversion seems to be extremely fast. If you look at the social signals, which is greater than 1, then exactly the same equations are still true. But no, these terms converge to infinity because R is greater than 1 and T is increasing. And therefore, the analysis of this is different. And essentially, what you have is that all these market share except 1 are going to converge to 0. And so you go to essentially monopolies in general. The inner equilibrium is still there. It's still a property. It's still an equilibrium, but it's unstable. You can show that essentially one of the eigenvalue of the Jacobian of the function f is positive. And so what this means here is that the convergence really depends on the initial appeals, and you don't know which monopoly you're going to get to. So if you look at the results, this is what you see. Once again, you can see that when you optimize or use the quality ranking in this particular case, you are better than the popularity ranking. And the more R grows, the more the difference between the popularity ranking and the quality ranking is increasing. And also what you see here is the predictability results. And once again, as long as R is smaller than 1, everything is predictable. When it gets when it gets greater than 1, and this is 2, even when you use the quality ranking, you introduce unpredictability inside the market. And the popularity ranking is completely unpredictable, as Watts and his colleagues have actually shown. So let me conclude. So we started with this paper. which was very interesting because it was basically showing you in a virtual setting and analyzing and showing you that if you do the natural thing, which is this popularity ranking, you get inefficiency, unpredictabilities, and increase inequality in this market. And I want to actually come back to some of the things that Watt says when he summarized the results, that the best songs never do terribly and the worst songs never do very well, but any other results is possible, and that the dynamics cannot be manipulated easily. This is obviously completely true in what they have been doing, and this has been replicated by many people. So they also actually look at why this is the case, and I'm not a social scientist, so I can't choose between these arguments, but one of the things that they were saying is that inequalities and unpredictability are inherent to the market, essentially, and it's very difficult to understand where the market is going if you don't know if you know only the individual preferences. But this is only true, if you do exactly what they do. If you actually do other things like, the optimization approach or the quality ranking, then it's completely predictable. The best song is always going to do the best, do the best if R equal 1, and the best songs are always going to do better if the social signal is less than 1. And the dynamic can be easily manipulated. In a sense, you use optimization or the quality ranking. So it really depends on what you are doing algorithmically when you present the market to the users. And social influence is always beneficial if R is equal to 1. It's true empirically when R is between 0 and 1, but we have counterexample showing that it's not always true. And the market is obviously fully predictable as long as R is smaller or equal to 1. So in a sense, if you look at what they did in the music lab, they did the natural thing. They ranked by popularity ranking. They ranked by popularity, which is what people would try first. But the key point is that popularity is very different from quality. And what mostly we are doing when we are optimizing or using this quality ranking, we are basically aligning popularity and quality and making sure that the popularity is actually reflecting quality. So there are many open issues. So the first one is that social influence is not always beneficial when R is smaller than 1. We have counterexamples showing that it can actually be detrimental. But typically, this is when the appeal and the quality are already aligned. Then you basically, the best product is not as good as it should have been. It gets a smaller market share. But the nice point here is, in this particular case, is that you can actually test before, because we know the equilibrium. So you can test what is the expected downloads at the equilibrium, and whether you use social influence or not. And so you can decide what to do beforehand. Optimality, we don't know what is the optimal ranking. The quality ranking is not optimal. Actually, it's very interesting. So we have a counterexample where you put the best product on top, but the second product is the worst one, such that you maximize the share of the best product. So we don't know what the optimal ranking is. And obviously, we need more complex model for actually when the participants come from different utilities and so on. We validate this experimentally using also large-scale experiment, but more needs to be done there, because we could replicate some of the results, but not all of them. These things take a huge amount of time and resources. So that's what I wanted to tell you, and I'll be happy to take any questions if you have some. So thank you very much. Yes. So what we do is we do this sampling approach. So we basically sample at the beginning, and we can estimate it very quickly. I could show you convergent results. Very quickly, we can actually estimate the quality of the various products. So we can do that relatively easy in this particular setting. Whether this is true in all settings, I don't know. But in this particular setting, we can just do sampling and determine the quality of the products. Yes. Steve, you had a question?
Right, so it's segmentation. Do you have any comment on if people are fed their information bubble? People live in their own information bubble, and then they have realities that they intersect. Does that correspond somehow to your segmentation?
Yeah, so if we can actually find out in which bubble they live in, then we can optimize for that particular bubble. I'm not saying this is good, right? But we can optimize for that bubble, and then we are optimal with respect to that bubble. I'm not saying this is good, but this is what you can do from an algorithmic standpoint. So I think if we can find out if we can find out who people are similar with respect to their taste, quality, and appeal, then we can optimize with respect to that. And that's the results that I've shown you. Yeah, so we can learn that. This is one of the things that is nice. You can combine that with machine learning to know, what are the preferences of a group of people and things like this.
the same as
Okay, thank you.